Okay. Okay. So, very good evening to IPSC delegates, IAPT members, students, and faculty members coming from various colleges and universities to attend today's talk. This is the fifth PRL-IAPT Dr. Vikram Sarabhai lecture series lecture, which is being organized today. And the speaker of the day is Professor D. Pallamraju, Dean and Senior Professor PRL. It is just a coincidence, or I will say it is a pattern now, that the first PRL-IAPT lecture was held in 2019, then 20, which was coincided again with IPSC, and today again it is coinciding with IPSC. Last 2 years, because of pandemic, we could not have this lecture in person, but now this year we are having this in person. The elements or the topics covered so far are planetary missions, hydrology, neutrino physics, exoplanet, and today we are going to listen about space science. So these are the coverage of topics. I would like to invite Professor Ken Joshipura from IAPT team as well as retired head of the department physics, SP University, to say a few words about this lecture series. Professor Joshipura.
Thank you so much, Abar, Dr. Bushit, and what a pleasant surprise. I never expected myself to be here, but our director, Professor Anil Bharadwaj, is not here at the moment. So let me initiate a few things. And I would begin with a question with which Dr. Anil Bharadwaj would begin. He would say to an audience like this, Kem cho bada? And the answer is Majama. I remember 2019-20 in the actual program, he used to begin like this. 21-22, it was online, and now again here. Professor Anil Bharadwaj has been a friend of mine because he has been working in planetary science, planetary modeling, and we have some interest in processes, atomic molecular processes, electron impact, ionization, and so we were in touch with each other. And then he came over here. So one fine morning, on behalf of IAPT, I requested him to see if an annual lecture series can be organized in PRL. And that was 2019, the birth centenary year of Dr. Vikram Sarabhai, the founder of PRL and the father of our space program. He, Professor Anil Bharadwaj, readily agreed, and he suggested that the name of the lecture series should be PRL IAPT Dr. Vikram Sarabhai lecture, the annual lecture. We are very happy. We are so much happy that IAPT has to just propose, and almost everything is being done by PRL. So thank you for doing all this. Very nice of you. All the speakers. The first speaker was Professor Anil Bharadwaj. He spoke about India space program. And then Professor R.D. Deshpande talked about hydrology. So from space to Earth, and then matter and neutrino and all that. So gradually, Burshit, it seems we are covering Prithvi, Pani, Agni, Vayu, Akash, and Agni means plasma also. And in that way, we have covered the whole universe in 5 lectures. Now, what do? We will start again. So thank you very much. I welcome the delegates of this conference. I welcome IAPT people and the youngsters and all those who are coming over here. Some of my past students are here, including Dr. Bushit. And so thank you very much. Welcome. Thank you. Dhanyavad.
Thank you, sir. I would like to now invite the president of IAPT Gujarat chapter, that is IAPT RC7, Professor PC Vinod Kumar, who is an alumni of PRL as well, to say about IAPT as well as to introduce today's speaker. Professor Vinod Kumar, please.
Good evening to all. It is nice coming back to this institute on certain occasions like this. It's really very encouraging for me to be part of the audience where I have been once, here as an alumni of this institute. First of all, before beginning, I would like to express our gratitude to the director, Professor Anil Bharadwaj, for timely nominating an appropriate speaker for this very important lecture series in the name of Dr. Vikram Sarabhai. It has been a flagship program of this RC07, started from way back 2019. And then I heard that this is the fifth of such lecture being arranged under the combined sponsorship of PRL as well as IAPT. To start with IAPT, to give few words about IAPT, it is the Indian Association of Physics Teachers. It's a national body to encourage physics teaching, to encourage the students who is opting for physics, and also to develop and create certain teaching learning tools in terms of books, in terms of magazines, in terms of arranging certain competitive examinations at the national level. It has started in way back 1984. IAPT has been initiated by very few members, maybe around few tens of members. And now we have reached to around 10,000 life membership of this association. And I hope the many young people here who are not a life member of such an association where your bread and butter is being initiated, being a student here, student of physics here, not necessarily be a teacher who is teaching physics. Everyone who is dealing with physics or who is dealing science in general are one or the other way a learner and a teacher of physics. So with this, I request many of you, young students who are not even reached to a position, if they can, it's a good organization that you can be part of this and be a life member of this organization. When I became a life member, it was just 250 or maybe 500 rupees as the membership, but now it has reached to 2,000 rupees. But then at that time, you know that I started my research career here with just 750 rupees as the scholarship. So you know that now things have changed. The value of the rupees have also changed. So don't wait for you to get a position after maybe after 5 years, 10 years time, and then join. So join right away wherever the association you find it is your career related. With this brief introduction, there are many other activities of IAPT. IAPT has divided into regional councils or regional centers, and there are around 22 regional centers all over India, and they are all active. They are free to plan out their own activities, basically focusing on physics education, physics learning, physics teaching and learning programs. And I very proud to say that IAPT's certain examination at the national level for the students are actually a selection procedure for the Physics and Astronomy Olympiad. And so far, there are many Physics Olympiad international awards are being awarded to Indian students. So Indians have coveted those awards in both physics as well as astronomy. So with this, I think it is now time, without taking much time, it is time to introduce today's speaker. Today's speaker, to introduce him is also an honor to me because he is also an alumni of this institute. And on behalf of the RC07, I feel proud that I'm introducing one of my colleague in this institute. The speaker, Professor Dr. Degirala Pallamraju, so commonly known as Pallam or Pallamraju, without really knowing what is D meant for. He is a professor of space and atmospheric division of this institute. He is presently holding the Dean Academic of this lab. He did his MSc from Osmania University, Hyderabad in 1990, and did his PhD from PRL in 1996. After a few years of postdoctoral fellowship in the institute as well as outside USA, he has returned back here about 10 years spending at various capacities outside India, and he has joined back here as a scientist at the Physical Research Laboratory Atmospheric Science Group. As far as the scientific interests are concerned, Professor Pallamraju is a well-known space scientist. He is known for his work related to space weather effects, geospace, vertical coupling of atmospheres, upper atmospheres, wave dynamics, plasma, neutral interaction during the geomagnetic storms, and exploration of new methods to investigate the upper atmospheric dynamics. So it is very appropriate that, as the Professor Joshibira Sahab has mentioned, that from the lecture series, we are covering largely the 5 elements, basic 5 elements, and space science happens to be one of such elements. So I think without taking much time, between you and Dr. Pallamraju, I invite him for delivering this lecture. Thank you very much. Don't be carrying the mask.
A very good evening. Thank you, Professor Vinod Kumar, for the introduction. I would also like to thank both, PRL people who are involved in this selection and IAPT for giving me this honor and opportunity to be the speaker for this year's PRL-IAPT Dr. Vikram Sarabhai lecture. As we are entering the 76th year of our foundation, it's all the more, I feel very privileged and fortunate to be talking in a lecture on the name of Dr. Vikram Sarabhai, who is the founder of PRL. I was actually pleasantly surprised when I received the letter from Dr. Prathul Desai saying that, that I should be giving this lecture. So I thank you, IAPT, and all the concerned for giving me this honor and opportunity. So again, being held in the auspices of IAPT, I have tried to keep this talk mostly into the physics aspects. So my attempt will be to talk about the way things, several of these words that you are going to see may be new, and it will be, I will be putting it in a very, basic terms as much as possible. So I will kindly request, the experts in the audience to kindly bear with me if I'm, talking to at a very, very basic level. So the way I have, spanned out is that I'll very briefly talk about what is the space research. What do you mind? What do I mean by that? And we use the Earth's or any planet's, terrestrial natural light sources, which are air glow and aurora. So those vary at that region depending on the dynamics happening in that altitude. So we'll use it as a tracers and uh, to track what is happening in the space. And while talking about airglow and aurora, there are these emissions are there in the daytime as well. So PRL has the unique, the legacy of initiating a new field of daytime aeronomy. So probably I thought that giving a lecture here under, in PRL and the name of Dr. Vikram Sarabhai, I would like to probably, span out the kind of innovations that have been done. And they're all very basic optical experiments. So I'll just show you. It's a kind of different arrangement of optics, then you get a new instrument. So that is something which I will like to draw your attention to. I'll attempt. And building an instrument has no meaning unless and until it produces science results. So I'll browse through what broad results that these techniques have provided. So with that background, say we look at stars, and stars are visible to us because the Earth's atmosphere is transparent to the visible regions. So they allow this visible light. And but starlight, we all know that it's emitted in all wavelengths. And but we don't see all the wavelengths. This is a picture of our own nearest star. And you can see that it has a 11-year cycle. It's in soft X-rays. And then this, in the same way, every star will have its own cycle of increase in the flux in various domains of spectra. And if you see in the case of, in the Earth, these are the optical window that I'm talking about. This is a light that reaches Earth, is near UV and visible and IR, and various, radiation, various wavelengths are absorbed at various altitudes. And so you see that as the ionosphere is formed because of that, because these X-rays are absorbed by different altitudes, and UV is absorbed at another altitude, and it forms, there is a heat release, so you get a thermosphere temperature larger there, and then ionization is formed, so you have ionosphere is formed. So again, this analogy can be applied to other planets also, because we have the august audience of IPSC sitting here. So I think this kind of scenario is going to happen in different planets in different ways. So this is the optical window. That's what I'm trying to use. And again, the ionosphere thermosphere is coupled because they share the same volume. So whatever is happening in the plasmas gets transported to the neutrals, and so on and so forth. Another aspect is that Earth is a magnetized body. So there are magnetic the field lines, which makes the ionosphere a kind of more anisotropic. The motion, plasma motion is different in different directions. So this creates a lot of interesting space processes, which are purely electrodynamics, plasma physics processes, and they are different at different latitudes. And then what I'll show you is that I'll try to address those things in a gradual fashion. So we know that there exists, because stars are there, we get able to see, but there is air glow. Believe me, there is air glow in between stars and are on the surface of the Earth, and it is not seen by the naked eye. But how do we know it? We know it through its cousin, the aurora. Okay, the aurora is if you want to know what is aurora is formed in high latitudes due to interaction of energetic particles coming and hitting the Earth's upper atmosphere and then energizing the atoms and molecules to their higher excited states. So these are nice pictures of aurora, but what you see here is that you can see as a physicist, you can try to see there are different colors there, and you should ask why different colors. You can see this whitish color there means that there is the both all the primary colors are there. So that's why it's forming white. And then there are rays, which is essentially means that particles are entering. And then sometimes it's all red. Historically, Romans thought it's all blood in the sky. It's a bad omen because there used to be a lot of wars in Europe. So, and then there used to be, if you see the other features, is that you can see the top, the red here, and then there's the bottom purple here. Again, as a physicist, one can ask, why the colors are there and where they are. And the reason is this, our aurora is like a really cosmic cathode ray tube, wherein electrons are energized and then they're modulated by electric fields there, and then this goes and this electron hits the CRT screen with the phosphor elements, gives rise to light. The same fashion, Earth's analogy is that there is a magnetic field lines here, there is a power source, a solar magnetosphere generator, particles get energized, they go and hit the high latitudes, and then you can form what forms is aurora. And then all planets with magnetic fields will have auroras. Okay, and this is, as you can see, it's a complex, result of various things happening between the sun and the Earth. So just looking at aurora, just as I said, what physics can we learn? We can just get the clues here that ground-based observations, we are looking at aurora. There are magnetic needles, are deflected when these auroras are happening. Often the rays are along magnetic field lines. So you can see that particles are coming along. So we all have done the magnetic filing experiment, with a magnet and iron filings. So you can see magnetic field lines. But here in the case of aurora, directly magnetic field lines are visible along this region. Analysis of color reveals energies of particles. Different emissions have different excitation energies. So if you are seeing a color, then that means that the particle that has hit and excited them has got that kind of energy. So in summary, you can see that we are already into the topic of space research through optical window. So that's what we are looking at. But now you can say, that aurora is so bright we can see, but what about air glow? Air glow also, you can see that if you take all the skylight that is coming in due to zodiacal light, stars, diffuse galactic light, and then you calculate, the astrophysical sources and then remove them. This is the kind of percentage of air glow that exists in the sky. In all these bands, you can see 55, 38, 53, 56%. So you can see roughly around any window, if you take around 50% of the nighttime sky that we see is air glow. Just to summarize, air glow and aurora is the luminosity of an atmosphere. When the initial excitation source is solar photons, it's called air glow. And the initial excitation source is energetic particles, it's called aurora. So we'll just use the word emissions here. And there are several emissions. This is a space-based measurements. There are several. This is 1200 angstrom here, and this is 9000 angstrom. So if you see, there are various emissions from various species, atomic, molecular species, their ions, and so on and so forth. And different emissions, I just showed only a few here. Different emissions occur at different altitude, and that happens because different emissions appear at different altitudes because the reaction rates are different, the constituents are different in densities, and the reaction rates and lifetime of a excited species, all these decide at what altitude a particular emission will be. So you can see if you are monitoring one particular emission, then you can say typically at what altitude the dynamics are taking place that you can, that's what you can infer. And you can carry out measurements from various domains, from platforms, satellite, rocket, and ground. Ground-based, again, this air glow is always existing all the time because the reactions are happening all the time. So nighttime, twilight time, and day glow, daytime. So I'll talk more on day glow here because that is a newer element that has initiated in PRL. But then this kind of observations have been have been there from at least more than 100, 120 years in terms of night glow. The daytime, it started 2-3 decades ago. So when you want to measure the daytime emissions from the ground, the issue is of the background contribution. The whole thing is that you need to take out a big elephant, and then you have to see what is the mouse sitting on the top. So there have been various experiments done in the past. I'll come to that, but just a browse through in terms of why do we actually need to monitor the air glow at all? Because we can see that it's called a passive remote sensing. We can just sit on the ground and look at what is the neutral density variations, what are the neutral temperature and winds, how they are varying, gravity waves, tidal behavior, plasma neutral coupling, and large scale waves, vertical coupling, several things that you can take. That I have still not exhausted that. So how does one measure these emissions? And we have, I'll just, with all the optical components that we all have seen, this is something that we use, just you have lenses, mirrors, detectors, filters, prisms, gratings, Fabry-Perot, and these are all the things that any physics lab of graduate lab will have. So these are the things that we use. This is the schematic of a typical optical system, and not all optical system may have all these kind of components. We'll have simply, aperture, you have to collimate the beam, hitting it a filter, just because you have to identify a small region that you are interested in. You need to separate out the wavelength, so you need a dispersing element. It can be anything, Fabry-Perot, gratings, etc. And then you have to focus the light and falling on detector. And detector can be, unidimensional or two-dimensional. So this is what it is. Nothing, really big. It's you need to know only where to put what and things like that. So next is this I already answered. Error exists in the daytime. Yes, it exists, but the problem in measuring it is the background solar continuum. So there are various advantages of looking at the daytime. Also, that is, you take any region of the Earth, integrate it for over a year time. 50% of it is daytime. Okay, because sun solar zenith angle smaller than 90 degrees is daytime. And then there is actually for nighttime, real nighttime is solar depression angle should be greater than 20 degrees. So sun has to go down. So if you remove that, that's a kind of twilight and all. It's remove that, then you have remaining percent is 38% is the nighttime. And out of that too, even this optical instruments are so sensitive that if there is a moonlight there, then it saturates your detector. So you operate only during full new moon plus minus few days, few nights. So what all knowledge we have in terms of the space dynamics is in the order of 20% of the time if you're looking at only night time. So there's so much thing that needs to be understood. So that's the motivation for daytime. And I'll put on record what kind of interesting innovative techniques that were used in the past, because the whole issue is to remove the solar background. So this is one of the first technique was used in 1960s, which was kind of a scanning polarimeter, because they use the property that day glow is unpolarized light, while scattered solar light is polarized. So for a spectrometer, they have taken one half of the slit covered with a polarizer and another with an optical attenuator. You chop the light between these two alternately, and then once you equate the counts, because at that time they were having unidimensional PMT kind of detectors, so that's why they were chopping the light from the slit to get alternately the light from the polarizer and from the optical attenuator. Once they are equal, then the difference will be the fluctuation in the unpolarized light, which is day glow. So that was what that thing that they attempted. Idea was innovative. However, as the cancellation of scattered solar light is highly angle dependent, and so no further measurements are possible. Next one was in terms in this again in the 60s, there was sodium vapor cell approach, wherein they use the property that the sodium lines are resonant lines. So what they had done is that they had put a sodium vapor cell and allowed the skylight to pass through the sodium vapor cell, and this they fluctuated. They employed a magnetic field, and then they subjected this sodium vapor cell to magnetic field up and down varying. We know as physics students that any magnetic field will produce a Zeeman splitting in the sodium lines in the sodium vapor. So then they use the light coming out of the vapor cell, whether it's when it is magnetic field is on and off condition, and try to get the difference and say that this is the day globe. Again, an innovative idea. However, the technique was restricted to resonant lines only, and further direct sunlight contribution, cannot be ruled out. So that way it didn't take off further. Later on, slowly, as you can see, we are, in again 60s, the low resolution etalon and an interference filter was used. Again, and another one was in the combination of scanning high order etalon and a low order etalon serving as a monochromator. These etalons all work in interference domain interference condition. So if you are changing the pressure of the etalon, you are actually scanning wavelength. So they use that as a monochromator. Again, nice attempts, but not successful in obtaining unambiguous estimates of day globe. Again, somewhat further, as you can see, we are progressing ahead in time. So people had the advantage of what has happened in the past. So people had come up with polyetalon pressure scanning interferometric optical spectrometers. So it's called PEPSIOS. And again, this another design which were reasonably successful. They produced one result. I think there's only one paper, and afterwards there have been no more research done because of strict alignment issues, very high, stringent alignment issues. Another one was in terms of SOFD. This is a design which is again, they use triple etalons, 3 Fabry-Perot etalons, one next to the other, again of different resolutions. Design is similar to another instrument called HRDI, which had been flown on URS satellite. So, but they have implemented that for the ground. And the satellite doesn't need to worry about the background, because background is more when you're looking from ground upwards. So this was a successful result, successful experiment. However, they're awaiting science results, but this is a nice technique. Later on here, coming to in PRL itself, there have been attempts in terms of Fabry-Perot instrument along with radial chopping mechanism. This was developed for tracking the artificially released lithium clouds on a rocket. And this was again, nice promising concept suitable for bright emissions, which because these vapor clouds are much visible to the naked eye, but it's in the daytime still. But the background of skylight is blue light, so there is a contrast that is available. But day glow is much fainter, and issues of with obtaining differences between the signal and the background existed. So later on in late 90s, close to 90s, there is a day glow photometer. This is one of the first successful technique for daytime air glow measurement that was developed in PRL. And this is PRL's contribution to the field of aeronomy. And since then, a new field of daytime optical aeronomy was born in PRL. Several results from such technique have been obtained and are being obtained even now. And as I said, having a technique and not having results, doesn't, it's not much of use. So I'll just briefly give you what is the approach here. Here, a low resolution, etalon is used as a high resolution spectral filter. So basically, the whole idea is that of interference condition has to be met. So what these people came out with was a interesting concept of stator and a rotor. One is a stationary, another one is rotates on top of it. And then you can, so now that you can see that there's radially one is rotating on the other, the whole basic idea is to have the interference condition when it's matched, and for all the conditions that are same. So if you're going away from the center, only the factor that is changing is lambda. So you have the light, you can see that light coming from inner region here, which is, if you tune it to the signal, then you have the light from inner region. There is a null region, so there's no contamination. Now light is coming outer region, and then from inner. So this rotates. In that, this rotation happens at very high speed of 1400 RPM or so. And you can really get quickly the light coming from inner and outer zones, which translates to signal along with the background and only background. So this quick separation brings out the daytime air glow. So this was a wonderful concept, but this particular instrument was suitable for only one wavelength. So we want to make it multiple wavelength. Another innovation was brought in terms of spiral mask, which this is what is shown here. And because the different wavelengths will have different radial distances, but the spiral mark will take care of that. And this instrument provided the first measurements of daytime aurora. This was an expedition which we started in Antarctica in 1993 and 94. We had a lot of interesting results coming out of daytime aurora from Antarctica. So far we discussed techniques with small field of view. But as you can already imagine, there is a lot of things that you can do if you have field of view is larger. And so we use shell gratings for that. And this is an instrument called HiRISE, which is high resolution imaging shell spectrometer. And this spectrograph, actually, this is the heart of the system is this grating here. And then it disperses light in, this is a shell grating, so it disperses light in high, large angles. So you get a spectrum here, you can nicely see there is a wavelength here, and y-axis is the space. So it's an imaging spectrograph. So you can get light from different, large area. The field of view is 140 degrees. So here you can see in the twilight time, this white bright light here compared to the dark lines here. These are all Fraunhofer absorption lines, while this bright line is emission. So that's where the red line, emission from oxygen is present here. So when you compare that to the solar spectrum, you get the difference between them, and that's the day glow. So, and that you can do it from different regions, so you can get what is happening in the space. So there's another picture. Nicely, you can see that this is morning twilight and this is evening twilight. So wherever the background is less, this becomes visible to the eye. But when the background is more, we had to do some more analysis to bring out the daytime air glow. So we wanted again to go for not single, this was single wavelength. So now we wanted multiple wavelengths, large field of view. Again, we used an shell grating, and then shell grating, the problem is there is a lot of order overlap because you're using at high orders. So M1 lambda 1 is equal to M2 lambda 2 at multiple places. So you need to understand very clearly where you have to, what the lines that you're interested in, and strategically find out, put the filters in those locations. And that's what is called as mosaic filter. So once we did that, what we have is that HiRISE has become MICE, it's multiple wavelength imaging spectrograph. And here, remember that I told you that different emissions come from different altitudes. So here we are getting emissions from three different regions, 630. These are some numbers. These are wavelengths actually of the emission, air glow emission that is coming from the sky. And you can see all the three wavelengths, very varied. Normal gratings, you can't get these varied wavelengths in the same diffraction angle. But because of the shell grating only, you can get this. And then you can see, you can simultaneously scan what is happening in terms of altitudes. So that is the advantage of this. So far we talked about the visible domain. Now This is an ultraviolet domain because we are looking at emissions that are coming from ultraviolet to look at what is happening in the Earth's upper atmosphere to see the wave scale sizes of the waves. So you have large field of view instrument, and then this is called UVIS, ultraviolet imaging spectrograph. And anyone in all physics students will know that, ultraviolet, it passes through any optical component, it gets absorbed. Okay, our glasses, are basically absorbers of UV light. So how do we do this here? We have done this by all reflecting optics. Nothing, no transmission element here. Everything is reflecting. So by all reflecting optics, you can do this, build this kind of instruments. And this, because ultraviolet light doesn't come to ground, so you have to go up. So we have put this instrument on board a balloon and then carried out this experiment from Hyderabad. And just for the sake of comparison, I would like to draw your attention to several of the experiments that have been flown here are listed here. And the UVIS instrument has the largest field of view and the highest resolution. Okay, all other experiments that I have gone in have smaller fields of view. So this is final test being done before that's final balloon launch here. And we got nice results in terms of the zonal gravity wave scale sizes that are responsible for, ionospheric irregularities. I'll not go into those details. But this was the first daytime launch for TIFR balloon facility also in their 40 years of existence then, because they were all doing in the nighttime. Because nighttime, the temperature gradients are less, and for the balloon, because these are high altitude balloons. So from safety concerns and all, they were doing in the nighttime only. But I said our science requirement is daytime. So this is the first experiment they have done in the daytime. So again, by changing the angle of the grating, the UVs, we changed it to near infrared spectrograph. So another instrument was born called NIRIS, near infrared imaging spectrograph. So why do we do that? Because there is, in the near infrared region, there are a lot of hydroxyl and O2 molecules are there in the mesospheric regions, which and we can get the temperatures of the medium by monitoring those wavelengths. So a lot of results have come about in terms of temperatures at the mesospheric temperatures sitting on the ground. I'll touch upon some of them. So the latest one is called the CDAP, which is a CCD-based daytime airglow photometer. This is nothing but a dayglow photometer, but now we have a array detector, so you can see very clearly. This is the spectrum or interference fringes formed on the detector. You can see the whole daytime spectrum there. We know what is the annular region of dayglow and the next region of background. So we can avoid this chopper mask that I showed you earlier in the design. So we can avoid that. We have no moving parts, and this is a suitable for highly unintended observations and also for space-based measurements. So such CCD-based and the array-based designs is proposed for airglow photometer payload on board the ISRO's Disha mission that even our ISRO chairman had touched upon in the morning. And another one, NAVA, is again for Venus mission, and these two are conceived and being developed. So these are just few glimpses of these instruments kept at different locations. I told you that magnetic field lines are there in the Earth, so different, and then the physics, ionospheric physics, keep changing if you go to different location because the dip angle keeps varying. So we go to different locations with these instruments there to understand what is happening in that altitudes, in that latitudes. So this is Guru Shikhar, this is our Thaltej campus here, this is Hyderabad, and so on. And that is the instrument being commissioned. These are the photographs of instrument. So in summary, what you can see is that spectrally we cover ultraviolet to infrared, resolution wise a fraction of nanometer to hundreds of nanometers, and field of view we cover from 3 degrees to large field of view. So in the visible, in the optical window, that is we are covering all these regions. Again, as I already told you also earlier, that building new techniques just the beginning. Once the instrument is developed, we feel very happy and contented that, okay, it's a large amount of work it's done. But that's where the scientist in us has to wake up and start using the, data or getting the, science from it. So several exciting, insightful, and path-breaking and trend-setting results have been obtained because this is a domain in the daytime which was not being explored earlier in detail. And again, until now it's all optical components, so probably a lot of things would be easily kind of digestible. But the space weather or not the space phenomena, I'll not go into detail, but I'll just try to give you a flavor of the kind of results. One of the important results is in terms of the vertical coupling of atmospheres. I showed you the picture of sun, and then it has a solar 11-year cycle with solar energy increasing and decreasing. The whole ionosphere thermosphere was thought to be dependent on the solar forcing. It's larger than the influenced by solar forcing alone. But in 2009, that was the deepest solar minima. And during that solar activity, that solar cycle, solar activity was very low. And there were a lot of results in terms of vertical coupling from below. So this new field has come out as a kind of, as an offshoot of the sun being, not very active during those decades. But then a lot of effects have come up, have been shown, and in our observations, from results from mice, is the primary data obtained is from mice. What we kind of parameterized that the ionospheric thermospheric effects will be larger. The solar forcing is greater than what is called as sunspot numbers, is greater than 110. If it is smaller than 35, the whole forcing is from lower below. And then there is a transition region in between. And then this is again a frontier area of research wherein, one can really dwell how much, what is happening between the 35 to 110. Another result, because now we talked about vertical, now I'm talking about longitudinal variability. Because of Earth has geodynamo is varying, so the magnetic field strength is different, geomagnetic field intensity. So the kind of nanotesla you measure on the Earth, because we all know from equator to pole, the magnetic field strength changes. But longitudinally also there is a change. And because Earth's ionosphere is a plasma, and then there is a lot of electrodynamics that takes place, the B here, the magnetic field, going in that altitude, when it changes, all the E cross B drifts on electrodynamics, everything keeps changing. So you can expect longitudinal differences because of B. And then there is, again, magnetic angle changes one can expect. And then various convective processes, you can expect longitudinal changes. But until this work, again, by us here, and then there is people, or the results were that longitudinal difference exists until 10 degrees in longitude, not smaller. So we asked the question, can they exist in the smaller region? So again, it's a large field of view experiment, so we kept it in the daytime looking at in the zonal direction, and because we wanted to see longitude. So we saw that the variations in the eastern directions are different from the variation in the western direction. That means that there are longitudinal differences. What is the separation? Because we're looking at different altitudes, and as I already told you, that this is in green line emission comes from 130 kilometers. So the distance is around 300 kilometers only. So you can see that the longitudinal difference do exist. So vertical happened, now it's zonal, and now let us go to meridian, from high latitude to low latitude. Okay. Again, there are features in the Earth's stratosphere called the stratospheric warming. Sometimes in the winters, here northern hemisphere winters, the polar latitudes, temperature increases. And then, and let us not go into the details of the processes there. But when that happens, when we were observing from mice from Hyderabad location here, low latitude, we saw that all these day glow emissions were going up. Then we postulated that there should be a physical motion of neutrals coming from high to low latitude and the kind of wind circulation. And that indeed has been followed up, and then later other models also do show that this indeed is the case. So this is another dimension physically in terms of what kind of results that have been obtained. Again, during those times itself, we were observing this from NIRIS from Mount Abu. We saw that the temperatures were larger when the stratosphere was warming there. So I said, what is happening? Stratosphere is very far away. But again, that led us to take up large amount of data sets from 12 years of data. And then we saw that we discovered that again, there is a kind of double humped structure in temperatures in mesosphere. So these new findings have come from these kind of measurements. Again, when there is a convective storm here, when thunderstorms and all, it's known that because atmospheric density decreases as you go up, the waves that are generated will go up. But then there is no experimental evidence for that. But because, again, all our instruments here, this NIRIS and CMAP here, which are operating from Guru Shikhar, again, these are all unattended instruments operating. Based on that, we could see that when this storm happened, Nilofer, next to Gujarat coast, and we could see that there is a propagation of waves going up into the mesospheric altitudes, at least until 90 kilometers. So this is one of the first experimental evidence or proof that waves do get generated during convective storms and go up. So this is another result in terms of because the whole electrodynamically, the electric fields, can't be generated, can be generated, but totally it's a curl of E0 around the plasma physics around the globe. So you see that the electric fields are eastward in the daytime and westwards in the nighttime in a given location, longitude. And using that property, we saw that, the airglow emissions track, whenever the airglow emissions are decreasing or coming towards low latitudes because of, again, large scale phenomena. We saw that that is the time when the vertical, the electric fields, we can use this feature to derive what is the westward electric fields, which is again difficult to obtain by other, by simple means. So this is airglow technique is a simple technique by which we can get the temperature, the fields, westward electric fields. This is again another new result in terms of, because any wave is there, it is three-dimensional object. So we have large field of view experiments here in terms of, we carried out experiments in terms of zonal meridional direction. So we get the zonal scale size waves and meridional scale size waves and what's happening vertically. Then we have another method by using digisones, we can get the vertical scale sizes. So based on this combined measurements, we could get completely description of the waves in both three dimensions. And knowing that winds affect the waves, now that we have measuring all the waves in three dimensions, we could derive the winds also. So which is again one of the firsts in this domain. We go to different latitudes, mid-latitudes. When this is mid-latitude is reasonably well-behaved, region, and then, but sometimes you see that this kind of enhancements we're seeing in the day glow. And then we ask this question, why it is happening. There are no particle precipitations, there are no other additional features. But we saw that that was the time when there are something called a bigger phenomena called the storm enhanced densities. So these are large-scale convective maps here, and this is the location of mid-latitude Boston from where this data is obtained. And we saw that the whole upper atmosphere in high latitudes has been changing because of the geomagnetic storms. And so we are using this knowledge gained by not just in the science aspects of what is happening, but also in terms of the techniques. And then so we are proposed this kind of instruments on board DISHA. That is, DISHA stands for Disturbed and Quiet Time Ionosphere Thermosphere System at High Altitudes. This is going to be a dual aeronomy satellite mission. One is going in the, one of the satellites will be going high inclination, another one low inclination. And then we'll have several ionospheric and thermospheric parameters, including airglow, electron densities, electron drifts, and many other parameters that are going to be measured. And this is, we are going to measuring auroral X-rays, air glow, red and green, 7774 emissions, ionospheric drifts, neutral densities, and electron densities, electron temperatures, and air glows from various, wavelengths. And this is, as I said, is going to be a dual satellite. So this is Disha H is high inclination, Disha L is low inclination. And so these are the instruments that are already, in developmental stage. And so this is the air glow photometer will have its kind of V kind of configuration with 45-degree separation, looking at 630 nanometers and 7774 nanometers. And this is looking at different altitudes. Again, without going into the details of space, space science phenomena, this suffices to say that this combination will give us enormous information on the electric field variation during geomagnetic storms. This is another instrument that is called NAVA, which is going to go on the Venus mission, and we are looking at two different wavelengths there. Again, as I told you in the beginning itself, that there is air glow is a phenomena that's happening at different, in different planets, and the processes and dynamics can be understood by monitoring these wavelengths remotely. So this is so these are the two things that are going ahead. And this is a kind of demonstration that we have done in the lab, wherein all these space grade, this will be replaced with space grade components. This is a object here, and this is a image that's coming out, and this whole processing electronics has been developed in PRL. So just to summarize, new field of daytime optical aeronomy has been initiated in PRL. And what I had tried to give is again a brief account, historical account on the progress and development of various techniques. Again, we carry out our research using such techniques, and the techniques developed, that I had shown range from ultraviolet to infrared, 3 degrees field of view to 140-degree field of view, and low to high resolution. And several new results, which are trendsetters and path breaking, have been obtained. Again, I showed you dynamical vertical coupling, longitudinal coupling, meridional from high to low latitude. So all these large-scale dynamics are possible just sitting on the ground and employing such kind of techniques. They have been illustrated here in this brief presentation. And as already touched upon, that kind of this expertise and this the gained is being implemented in the future space missions of Disha and Venus. So I would like to acknowledge, as because these are all teachers, physics teachers and mentors. At this time, Professor R. Sridharan, my thesis supervisor, and Professor R. Raghuram has been a PRL, doyen of PRL in terms of upper atmospheric research. Some collaborators, from Supriya Chakravarti and Jeff Baumgartner, some past colleagues. We lost a couple of our good colleagues, Dr. S.P. Gupta and N.K. Modi, and some of the other acquaintances with whom we had various discussions, Professor Shekhar, Narayanan, Kedar, and Parsh. And I would also like to acknowledge Director PRL for all the support for coming up with, whenever we come up with new instrument, new technique we want to do. So we had been receiving very good support and encouragement to put it wherever we want to place that instruments. And PRL workshop, several of these instruments are developed in PRL in our workshop. So I'd like to acknowledge their contribution as well. And these instruments are kept at different locations under, with the collaboration from, in Hyderabad at JNTU, and data obtained, instrument is not kept, but data have, sets have been obtained from various, institutions like IIG, SPL, URSC, SAC, and NRL. I would like to place my, gratitude to them. And our budding, Disha and our team members who are very energetic. And to the IAPT for giving me this opportunity, and organizers of the fourth Indian Planetary Science Conference for accommodating this slot in their scheme of things. And some of my present colleagues and students who are always, from whom I'm always learning, because I want to be a student all my life. They're very budding with a lot of energy, a lot of enthusiasm, coming up with different, ideas and works. So to conclude, I would like to say that, space research or space weather or sun-earth interaction or sun-planet interactions is a frontier and challenging area of research. And I invite, young researchers and physicists, physics students to book their seat in this adventurous journey into the future. Thank you for your attention, and I'll be happy to answer any questions. Thank you very much.
Yeah. We also invite questions from our YouTube viewers through YouTube chat. In the meantime, I request Dr. Chetan Limbachia to conduct the question answer session.
Thank you, Dr. Bushit. Thank you, Professor Pallamraju, sir, for a fascinating talk. And the platform is open for questions. Yes.
Yeah, excellent, sir. I got a lot of things. And today's the literature, you can see the daytime air experiment. First references coming from PRL, from the arts present. Which we made a imprint regarding. And among that one comment like in the visa program. You have the lower orbiting, polar orbiting as well as it's action. Yes, use that thing. Because plasma properties they evolve in terms of minutes, within few minutes. I'm just adding a comment.
Okay.
Plus these two, plus geostationary. It means we are going to solve many problems. Then the second one regarding the plant. I saw your maximum going that fraction of the nanometer. I'm doing some numerical calculation. Shows that because of the CO2 contamination, we have to do much better than even fraction of picometer. Then to separate out that section. Thank you.
Okay. For the first one, I would, though it's a comment, I would like to comment on the comment that is air glow emissions. These are all coming from 200, 300, 400 kilometers. Okay. If you go to geostationary orbit, that is 36,000 kilometers. So if you take the intensity here and see the depletion 1 over r square, the kind of data or signal you get is very small. So from geostationary, I have not seen any experiments. But then there are on the high inclination orbits, are used, because they come from high to low, and then they have taken, the image satellite is a one which you have seen auroras there. Okay. From that, again, when it comes closer only, you'll see, and when it goes far away, you'll not see. Okay.
Thank you. Any other question? Yes, please.
The Aurora. So Aurora, they are basically the northern and southern lights. But the LEGO emission is happening through time. Now, actually, is there any study actually, how do you put actually Aurora can even happen in the daytime? So where actually the near simultaneous measurement of both the day glow emission from the space, of the is the particle, in particular Aurora. Any measurements made and how it is being delineated? Basically, how can we distinguish the
Okay. Yes. Yeah, there are results. Again, for want of time, I didn't I didn't show them here. I had the opportunity to take these instruments, both to Aurora in southern Aurora in Antarctica, and several experiments I had carried out from Sonderstrom, Greenland, and northernmost point of Greenland called Thule, and also HARP facility in Alaska, wherein we could see very clearly. We can very clearly see that when Aurora, when it is in the daytime, when it is Aurora or when it is not Aurora. There is again, there are various clear characteristics, differences in terms of spatial variations, in terms of temporal variations. So Aurora is highly dynamic. And then that you can correlate with the particle precipitation happening by other radar measurements, or rheometer, wherein you can see the relative ionospheric absorptions happening whenever the particles are incident. I have data, we have measurements and results which show that, ionosphere radio measurements blacked out because of the aurora. But then from optical measurements, we could see that the aurora was occurring because it's that kind of. So there's very clearly differentiation can be easily seen, and we have results on that.
Yes, sir.
Recently, it seems that huge solar flares are released. Do you observe any effect on our magnetic field?
Yes.
This
Yes,
recently?
yes. We do that study. We always see these effects very clearly in various, I just talked about the optical domain, but then there's radio domain wherein we can say ionospheric density is changing. In geometric field, field fluctuations do change. So the whole topic or whole research that we are doing is basically to understand the whole variations between the sun and the earth, and how the earth, the poor fellow, we see the brunt of all the things that are happening. But we have to live on the earth and use the space, infrastructure. All our satellites get affected because of this effect. But that's another domain which I didn't touch upon. It's called the space weather domain. So all our satellites are orbiting. And when these kind of geometric storms happen, even our satellites, which are trying to, so for societal applications, they get affected. So the whole area of research, again, this is also, I put it here in Sun-Earth, interaction or space weather. This is a frontier area of research wherein the whole globe, all people, any spacefaring nation should be doing this kind of research, and several nations are doing. And there is clear effects, and we know very clearly what is cause and effect very clearly now. The issue is in terms of when that will happen. Those are the advanced studies need to be done.
Yes.
With your latest CCD experiment, and high resolution gateway measure, if I imagine an experiment, imagine two similar instruments, one put on the ground, and either you take the balloon, which will go to 50 kilometers. So do you see any expected difference? Can we discover something, final features or final details?
You were talking about the same, the same wavelength, because this is meant for red line air glow. So, okay.
Yeah. Even nighttime, nighttime or daytime.
No, the emission I'm talking about. So if you just depends on the emission, so that is this red line emission, this is visible light, there's no attenuation in the atmosphere. So in principle, it should show the same effect between, ground and 30-40 kilometers away. Okay. The intensities also should be the same, because again, probably to answer just to connect to you and Dr. Thampi's question, day glow is more of is less structured, and it's kind of diffuse source. So, and therefore you are monitoring this from the ground or going up, the kind of area that you intersect is going to be the same. So you get the even intensity should be same in principle.
I mean, do we expect for night glow some difference?
No, in terms of if you're talking about night glow, there's no difference. Nighttime aurora, there will be differences. Night glow, there should not be any difference from either from ground or, because Earth's atmosphere is transparent to this particular visible wavelengths. Okay, talking about, because we carried out the ultraviolet experiment from balloon, because ultraviolet doesn't reach the ground, so we have to go to altitude where we get that emission.
Any other question from the curious students? Yeah. Maybe, yeah, anyone? Or meanwhile, yeah, you can ask.
Well, firstly, thank you for the question I have had for a long time looking at aurora is, we remember auroras as colorful curtains in the sky. So, could you comment on the dominant controls on the morphology of aurora as we see in our life? The curtain structure.
That's kind of very well documented, in terms of, when do you get there are called auroral arcs, auroral, particle, the arcs and auroral curtain, that's itself called curtain aurora, with a if you see kind of, the purple border I showed, it looks like a big curtain with a purple border. And so What is documented is in terms of they are confined in latitude, but then they are present in large longitudes, and then they are more in towards the night side, larger in number than the day side. Because night side, again, particles come from, from the magnetic tail after recombination, particles enter with high energies. So in the night side, you will see that them more. And then there are the kind of colors, you see the green line is basically 100 kilometers or so. And then the red line comes from 250, 300 kilometers. So people have taken the ratios of these emissions to get the energies of the particles. The purple below is basically due to N2 positive band, which comes from 85 kilometers. When you see purple, means that automatically that there is a high energy particles have entered. So that kind of inferences and calculations, estimations are all have been done, and the physics of it and the dynamics of it is very clear.
Yes. Is there any other question from the audience? Yes.
Sir, so very good lecture. And what about planetary auroras? Do you have any idea about it? And does it give any clue on any planet's atmosphere content or whatever?
Yes, it does. Basically, this whole aurora air glow is essentially they are kind of, are tracers of what is happening in that particular medium. So you can know about the constituents just looking at the color. You can, if you don't know anything about no measurements also, but looking at the color also, you can know what kind of transitions would give rise to that particular, color. So you can know what is the composition. And due to auroras, in fact, I think you should, in maybe a couple of 2 decades ago or so, there was nice picture of the Jupiter EO satellite of, Jupiter, natural satellite. It did causing a shadow, it comes in the magnetic field, and auroral shadow was formed because of EO. So there was, again, the kind of composition of EO was, was also was inferred based on this kind of measurements. So whenever you see any of these aurora, you can infer a lot of things that are happening on the atmosphere at that altitude. Venus, it's a question we'll have to see. The air glow is there definitely, because you need to have a magnetic field. That, as I told you. So because the Venus doesn't have magnetic field, so you will not see it as clearly as a nice auroral, oval you'll not see, but air glow is definitely we'll see. Yes. Yes.
So actually, if you look, aurora is a phenomena for which you need an atmosphere and magnetic field. Okay, there are 2 primary requirements. If you have aurora, that means there is an atmosphere and there is a magnetic field. Okay. Now, known magnetic planet, as Pallam was talking about, like Venus or Mars. Mars, we have seen aurora of all possible dimensions, which can even not happen on planet Earth itself, because Earth has a magnetic field, and therefore aurora happens in the polar regions or auroral regions. But on Mars, we see equatorial aurora, which is not possible on planet Earth because we have a magnetic field. Okay. Same thing is true for Venus. Venus has not been explored in that much detail by an orbiter which has that kind of instrument so far. But there are already conjecture based on finer Venus observations, and they talk about aurora on Venus also. Okay. So hopefully our Indian Venus mission will be carrying instruments which will be seeing aurora in more detail for the first time. Thank you. That's a question.
Check. Sir, during an SSW event, you said that there was a double hump structure in the mesosphere. Is it solely due to the warming that's happening below, or is it influenced from the solar?
It's nothing to do with the solar. This is purely from the lower atmosphere point of view. This SSW itself is a very large scale phenomena, and when the temperature is large, it can give rise to various nonlinear effects in terms of waves. So they are the ones which are coming towards, in the high latitude, you will see stratospheric cooling, heating is associated with mesospheric cooling on the Earth in high latitudes. But then what was new thing that we saw was that cooling there in mesosphere is associated with the mesospheric heating over low latitudes. That is the one which was discovered by our measurements from infrared observations from Mount Abu. So that's what we asked the question: what is happening? So then we dwell into various data sets of satellite measurements over 12-year of period, looking at all the SSW events that have happened, and we see that very naturally, there is a lot of very kind of double hem structure exists all the time. So that's a kind of new discovery. The one in the last.
Of two more colors, golden and silver. So what is the primary difference between aurora and the rainbow if we compare it million of years ago? Secondly, can we see aurora under the oceans also in 360?
Okay, there are, to answer that, rainbow and aurora are very different processes that are, one is due to the light diffraction through the solar, the water droplets happening from the sunlight, because of the sunlight, dispersion that is happening. And that will be in a very, structured fashion in terms of, because, the deviations of lower wavelengths is larger. So you will see the kind of very clearly ordered WIPGYOR kind of very clearly thing. But aurora is completely different. There's no, it will not have any of this kind of structure. The formation mechanism itself is different, wherein you have to excite an atom or a molecule to its higher state. And that energy it has to be given either through energy existing in the system at that time or energy coming in through external source, which is in terms of aurora has a magnetic field, the planet, and then particles come along the magnetic field and hit the high latitude atmosphere. So these two are different processes. And talking about aurora over in the middle of oceans, it will not happen in that because at any atmosphere, if there was no atmosphere, that again, that scenarios we can think of, but then there will not be ocean also at that time. But if you have, again, the aurora's particles don't reach ground because the density keeps on increasing as the particles in the Earth's atmosphere. So their energy is lost at around 80 kilometers or so in the case of Earth. So they don't come down. Yes.
Thank you, sir. We'll take a couple of questions from YouTube. The first one is, what is the benefit of these studies in looking at climate change?
Okay. There are, what we are looking at is the space climate. Okay. Because just as we are, bothered about what is happening, today, tomorrow in the kind of thing, the same way we are looking at the space climate, what is happening in the space, and we are going to be, we are affected by the space climate and the space weather in the shorter, time scales, and with the progression of humankind and the technologies, going to higher, next, neighboring planets and far and beyond. We need to understand the space climate extremely well. So these are all, just when, as I said, as we all know, when Faraday, discovered, this kind of, dynamo, then, he was asked, what is the use of this? Okay. So there are uses because these are all basic, fundamental sciences with a lot of great potential for applications. So we don't know which connects where, because earlier, until 20 years ago, people didn't know that lower atmosphere can affect the upper atmosphere. Okay, but now, so these are various new developments that are happening.
So another question is, what are the opportunities for undergraduate students to participate in these such research projects? And follow-up question is that how can they participate in data analysis of these studies?
Okay. For the first question, I will, ask the student, whoever is asking, or the person, just to be watchful in terms of projects that are offered, in PRL, and they can take up projects in PRL in any of these topics, or not just in PRL. There are several institutes in India. Whichever institute is closer to their house or their place and they're comfortable with, they should approach. And we want the undergrads, at that, to be involved with these kind of frontier science areas. And so they should be watchful of, they should look out for opportunities in all institutes. All academic institutes will have, one or other name. They may have names different, but they'll have opportunities to get to participate in.
So the other one is, can they do some data analysis
Yes,
studies?
okay, the second part was data analysis, but definitely. So this is also kind of inclusive of the first one itself, in a sense that if they are coming to a place wherein they are learning what is happening, they can follow up with data analysis. So there are these projects first, to get involved with this thing. These are generally not taught in schools and colleges. So they should come. I think most of the thing I attempted to put in what all basic physics students do learn in bachelor's and master's. With that knowledge itself is sufficient first to approach, to attempt to get into this kind of fields. So these two are related.
Thank you very much.
Is there any other question from the audience? I had just one small query, sir.
Sure.
When you look at the air glow from above, from the satellite, for example, how do you take into account the storms happening in the ionosphere?
In fact, we actually want to study them actually. So that's exactly what we want to study, how the storms that are happening in the ionosphere. And from sitting on the ground, we can see what is happening on our overhead, how the storm is manifesting over time. But when looking from space looking down on a storm or air glow due to storm, we know its spatial extent, how big it is and what is the extent. So that is one of the purpose of doing these experiments, is to understand exactly that in terms of how these storms manifest in the ionosphere, because the consequence of that is that ionospheric disturbances is has a fallout in the radio communications. So all our GPS signals are coming through the ionosphere. The ionosphere is calm and quiet, and you can predict exactly how the ionosphere behaves. Your GPS signals, the kind of corrections that are done are reduced. But if there are ionospheric storm is happening, airglow is just one of the manifestation of the storm. There are in radio waves, we can see several waves which are getting generated. There is also in one of the Disha mission, one of our aim is to look at those waves that are happening. What are the scale sizes of waves that are happening due to a storm? And various other manifestations of the storm is what we want to study.
Right. So thank you very much for a very fantastic talk. I just hand this mic to sir.
Yeah. Thank you, Professor Pallamraju, for a fascinating talk and very interesting discussion. Now we are moving towards the closure of this event. And before I invite Dr. Prathul Desai, Secretary at IAPT RC7, when we have function of IAPT of this level, one face is missing in the audience today is Dr. Tushar Pandya. He used to come around with a lot of energy and enthusiasm in terms of bringing young students with him. And he was very much active in all IAPT and GSA activities, whom we are missing today. We lost him in COVID last year. Nevertheless, I would like to now invite Dr. Prathul Desai for closure of the event, including vote of thanks.
Thank you, Dr. Bushit. we would like to, give away our memento to the speaker as well as Honorable Director of PRL on behalf of IAPT. So at the beginning, I'll request Professor Vinod Kumar to, as a token of our love, give a memento to the Honorable Director, Professor Anil Bhardwaj. Professor Bhardwaj, there is a Pradhani Tarang magazine, which is yearly publication of RC7. Yeah. Now, I request Professor Viresh Thakkar to do the honors. Please give book bouquet to the Honorable Director. Now I'll request Dr. Chetan Limbacha to give away memento to the speaker, today's speaker, Dr. Pallamraju. I'll request Dr. Puneet Suthar to give a big book bouquet to today's speaker, Dr. Pallamraju. Thank you, Puneet Bhai. So we are almost at the end of today's session, and I'm here to express the vote of thanks. As a Secretary, IAPT RC07, I feel honored and privileged to get an opportunity to propose a vote of thanks on this momentous occasion. On behalf of IAPT RC7, I convey my deep regards and hearty thanks to the Director of PRL, Professor Anil Bhardwaj, for patronizing this flagship program of IAPT. We feel proud and honored to be associated with PRL in this joint collaboration, which is blossoming into a synergic partnership because of the unflinching support and cooperation extended by Professor Bhardwaj. Also, I would like to extend special thanks to the distinguished speaker for today, a senior professor and dean, Professor Pallamraju, for sparing his valuable time and delivering a riveting talk today. Thank you, Professor Pallamraju, for highlighting several measurement techniques. You have covered a wide spectrum of techniques and deftly combined it into a short presentation. So thank you, Professor Pallamraju. I'm sure all of us who are in audience today would return home with fond memories of this wonderful occasion. Special thanks are due to Professor Ahluwalia, President of IAPT, for lending support to all the activities carried out by IAPT RC7. Special thanks are due to Professor Dr. Bhushit Vaishnav, Head Academic Services, who has over the years been a strong connecting link between us and PRL. Starting from preparing an announcement flyer for the program right up to this day, Dr. Bhushit has taken personal interest in giving this program its final shape. Thank you, Bhushit Bhai, for all your help. I would also like to thank all the technical staff at PRL who have made arrangements for live streaming of this entire program. A special thank is due to Dr. Durga Prasad for handling questions from YouTube and to Dr. Chetan Lindashya for conducting the Q&A session. To all those who are present here, I extend a big thank you. Without your presence, this program would not have been so successful. Your presence motivates us to do more. I would also like to thank all those people who have directly or indirectly helped us in making this program a resounding success. Thank you, one and all. Thank you. Sorry. I would like to request Professor Pallamraju to write an article based on today's talk for the upcoming Pradhamikaran magazine. Thank you. Thank you, sir, for accepting our invitation. Thank you.
So there is short announcement from IPSA. So as announced by Professor Anil Bhardwaj in the morning, so tomorrow there will be a general body meeting tomorrow evening. So there is a IPSA registration desk just outside opposite the registration. So I encourage all of you to just visit the desk. There are various membership options and also inaugural membership offers as well. So I request all of you to take this opportunity and get benefit from them that. So that and also join us for the general body meeting tomorrow evening. We will let you know the time and venue tomorrow. Thank you.
Okay, so thank you for your kind intention and good night. See you tomorrow all. One more announcement, please stay.
Hello. So for the IPSC participants, those who are going to Hotel Regenta and Hotel Creos, they have to contact Divendu. Divendu, can you just raise your hand so that they will know? And those who are traveling back to Thaltesh campus, they have to meet Somik and Satyanand. Somik and Satyanand over there. So after dinner, please contact them. They will take you to the bus and then you can go to your respective places. Thank you.